Okay, this project is called Obtaining Quantitative Information from Ion Mobility Spectra with Help of Artificial Neural Networks. And I will quickly explain what is ion mobility spectrometry and how do the spectra look and how can we use artificial neural networks in order to get quantitative information. This is a try. It's not sure whether it works, but it's also interesting to see whether artificial intelligence can be also used for these purposes here. So this is here a so-called ion mobility spectrometer. Actually, of all this, what you see here, the spectrometer is this little device here. The circle went a little up there, but this is what we want to use. All the other stuff here is here electricity supply. There are voltages for the detector, there are high voltages, a few thousand volts for the device, and a few other voltages, and all the white tubes that you see here, they're just there in order to provide this device with gas, because it is a gas detector. You use ion mobility spectrometry to detect gases. And mainly this means what gas is somewhere, so identification of unknown gases. This is then the qualitative information, but as always we would also like to know how much gas is there. And this is very difficult and has never been solved for ion mobility spectrometry, but there are advances to a conclusion, and artificial neural networks is one of these approaches, the one that we would like to test here. This is how ion mobility spectra typically look. You have always one signal here at the beginning, which is always there. These are the so-called reactant ions, so they actually do the job and ionize the analyte that we want to detect. And then you get such spectra here, as you see. And the characteristic information is actually after which time do we detect a signal, because this time can then be used in order to calculate the mobility of this ion. And the mobility is a characteristic quantity that you can then look up in tables if the substance is known, and hopefully find then there's somewhere a value that you can then use in order to identify the substance. We see here already that depending on the concentration, this is here parts per billion, so percent is parts per 100, we talk about here parts per billion. So for very, very low concentration, you see how here actually the relationship of different signals, the intensity of different signals changes. At high concentration, you see here, you have this one here quite strong, this one here also, then you go down with the intensity, then you see this one goes much stronger down than this one, or here it's actually not there anymore, but only this one. But there's another effect where you can go with another time domain that I do not explain here. But if you play with this, then you see that actually, depending on the concentration, the one signal here, especially the second one here, goes up and then down, or it goes up quite fast, or it goes up quite slow. And all this is data that you can then use in order to find out is there a relationship with respect to the concentration, so to the amount, how much substance do I have. We see this here clearly optically, like we look at the spectra, we clearly see the effect, but can we turn this somehow into a formula or mathematical description? And this is what we would like to try with artificial neural networks. Here you see these curves of the intensity over this second time domain here. And there you see that different substances here behave in a different way with respect to the concentration. Once again, a lot of data. And we have to see whether we can sample these data points and use them in some kind of artificial intelligence approach. Doesn't have to be neural networks, but this is where I would like to start, in order to find a clear relationship between spectrum and concentration. So the neural network can then be used in order to get some input and create some output. The output will always be the concentration. Input, maximum intensity, maybe the whole shape of the spectrum, maybe the whole shape of many spectra over different delay times, this other time domain that we have there. All this is possible, and out of all this we can create our neural network, and let's see whether this works. The problem is our training sample size is very, very small. So we cannot create here millions of samples or whatever. We know that always this kind of technology works if you have a lot of training data. This is what we don't have here, but maybe we still can find a solution. So this is the goal of this project. And this is the program that I would like to use for these tests. It's called Fast Artificial Neural Networks, FAN. You find this on GitHub, also on some other web pages. And the advantage is you load your data here, you set up here conveniently your neural networks, number of nodes, connections, activation functions, and whatnot that you can use there. And then I would like to see, is it possible to get out of this data that we have this quantitative information. In this project, you don't have to use FAN here. This is only a very convenient approach in order to set up a neural network if you feel more comfortable with using toolboxes from MATLAB or anything else that you found online from Google or whatever. This is all possible to use. In the end, I'm just interested to find out, can we find this relationship that we see there in the spectra? Can we use this in a little more refined sense? And maybe the neural networks see effects that we don't see. And this project helps you to see all the details when you set up such a network, whether it works, whether it doesn't work. You see the difficulties, the obstacles, so that it's not all so straightforward. So for people who have little to no knowledge about neural networks, this would be a nice start into it and work with it in order to see what is this technology capable of, and maybe just what is this technology not capable of. But this is the goal of this project.